I know, I don't care. All right, so we have a test tomorrow on 3 topics: optimization, linearization, related rates. Yes, I know it's scary, it's word problems, blah, blah. But I'm not picking problems that are bizarre. I'm trying to stick to the ones we focused on in class. All right, like through the class examples and homework problems that we went over. Yes. I think it's like 8 or 9. I don't know like exactly. There's a couple of each type. I think I have 2 linearizations, 1 differential, 2 or 3 optimization, and 2 or 3 related rates. Okay, the one that you have on your desk is a related rates problem. But I just want to be clear, so it's real easy, bless you. And even though it's, bless you, it's not due to the day you get back from vacation, you might just want to get it done because it's not bad. I didn't get a chance to put the cone problem on the test. I just ran out of, so I thought, oh, let me give them one that's a little more fun. So what you have for this little take-home part, I don't know if I want to make it a quiz or part of the test. I originally said just part of the test, and then the other kids were like, yeah, well, the other kids would say, no, make it a quiz. So I'm staying undecided right there. All right, but here's how it goes. You have eggnog flavored coffee. Because you wouldn't put that in a coffee maker, that'd be weird, right? All right, so you have it in this conical, cone-shaped coffee maker, and it's dripping down into the coffee pot. Now, the coffee pot is in the shape of a cylinder. The coffee maker is a cone. Now, when you have the coffee coming out of the coffee maker in the cone, we all know like the radius of the liquid's going to change, right? But what else is changing? The height. So you're going to have to label that with something. I'll leave that to you what to call it. Now, the coffee drips out of there, and it goes into the cylindrical coffee pot. Now, the great thing about cylinders is the radius going to be a variable or a constant for the coffee? Constant. Love it. So you can figure out what that is after you read the problem. But there is going to be something that changes the height. So don't name that the same letter you use up here, because these heights are not going to be the same. The height of the, whatever you call this, the height of the coffee in the maker, you should not call it the same letter. That'll mess you up. All right? And the only other words of encouragement that I'm going to give you, as a big hint, let's say you go through the first part and you figure out dV/dt for the coffee maker. Let's say you find out that dV/dt for the coffee maker is negative, it should be negative because the volume is decreasing, negative 2 cubic inches per minute. I'm just making that up, so don't, that is your answer. So if you find out for the coffee maker dV/dt is negative 2 cubic inches per minute, does that give you something for the pot? What would dV/dt for the pot have to be? That's what I'm saying. If you know the rate it's leaving the maker, you know the rate it's entering the pot. All right. Well, I wrote hint is there a relationship. I just wanted to make sure we all kind of got it. All right, so let's talk about this test that everybody's dreading, but you really shouldn't. Linearization just means approximate a graph with a tangent line. You write the equation of a tangent line. Let's do one of those. Okay? Sure, we can do everything you want to do. Do you want to do a linearization that's one of these problems, or you want a different one? Sure. All right. The day you get back from it, but if you want to hand it in tomorrow, well, you can do that. It's up to you. Okay. So for linearization, I could be nice, which I am in one of the problems, and actually give you the function and say approximate. Oh, by the way, the only formula you have to know for tomorrow's test is the area of a circle. What is the area? Don't tell me anything about that. Area is always measured in square units. So that's pi r squared, right? Length, circumference is a length, is measured just in units. That's 2 pi r. So you do need to know that area of a circle is pi r squared. And you have to know Pythagorean theorem. Any other formula I'll give you. I don't like that whole apple pies are delicious, because every pie is delicious. It doesn't make any sense that you would think you could just reverse that and have another sentence that's true. It doesn't. I just don't like it. It just seems random. All right, so let's say you're asked to approximate f of 3.2, and I actually give you, with a linearization, I'm just going to write with a lin, okay? And the function, or is anyone, if you need paper, I can put some out.
What's the volume of it?
1/3 pi r squared h. It's 1/3 the volume of a cylinder. I have paper here. You guys have, you can just send it back, send around, and okay. Let's have a function. Let's say, sorry, I already told you, ln can be linearization. What? X cubed? Okay. You want the +7? You got it. Okay, so we don't feel like cubing 3.2 and adding 7. We're going to write the equation of a tangent line. That's what a linearization is. Now, if I don't tell you where to write your linearization, you have to think of a number that's near 3.2 that you could easily plug in here and get an answer. 3. So you're going to come up with a linearization at 3. So to write the equation of your linearization, I'm just going to write this now, make sure you have it. To get the slope of your tangent line, it's going to be f prime of 3. Then what goes in the parentheses? X minus 3. And then we just took the y1 here, we added to the side, so it's plus. How do you get the y coordinate of the point? F of 3. So if you're going to write the equation of the linearization, equation of a tangent line. All right, point slope. This is just y L of x. Like you're used to seeing y minus y1 equals slope times x minus x1. Yeah, well, 3 is your x1, right? To get your slope, that's the derivative at 3. Y is, we just call it L of x. Okay, we put in function notation, L for linear. And y1, we added to the other side, that's why it's positive on the other side. So we just move this over and just put plus y1, that's your f. Right. So this is how you write the equation of a tangent line at 3. So you have to get f of 3, and you get f prime of 3. Let's get f of 3 first. What is f of 3? 3 cubed plus 7. What is it? 34. Okay? So you need to figure out that. This just stays the same. And then you need to get the derivative at 3. So what's the derivative? (3x squared). Okay, now we need to plug 3 into that to get the slope of the tangent line. Yes, it's the slope. So this is the equation of our tangent line drawn to this graph f of x at x equals 3. So instead of plugging 3.2 into our function, we're just going to plug it into the equation of our tangent line, because they're very close. So we can approximate f of 3.2 by just plugging 3.2 into the x, the L of x. So it'll be 27 times, and you don't even need a calculator. Well, a lot of times you don't for these, because you do what's in the parentheses first. What's 3.2 minus 3? 0.2. 0.2 times 27. Like, you know what 2 times 27 is, right? You just move the decimal. So well, 27 times 2 would be 54, so it should be 5.4. So it'll be 5.4 plus 34. Yeah, so it's approximately equal to 39.4. Now, if you're asked, hey, is this an under and over approximation, what are you going to need to know? Concavity. What's going to tell you the concavity? Oh, I was scrolled up. So if you didn't know the concavity of this was x cubed. You just get the second derivative. What is the second derivative of this going to be? 6x, right? So the second derivative equals 6x. You might say, well, that's sometimes positive, sometimes negative. That's true. But in between 3 and 3.2, for that part of the graph, is that part of the graph when x is a number in between 3 and 3.2, 3 is where I drew the tangent line, and 3.2 is the number I'm plugging in, is that going to be positive or negative? Positive. So is my graph concave up or concave down over there? It's concave up over there. So I just care about that part of the graph. So if I drew my tangent line and I use that, oops, sorry, that should be a little lower. There we go. Nice. Right. So my approximation, is it going to be less than the actual or greater than the actual? Less than, because the function is concave up there. Okay. So that's less than the actual value of. Well, no, because you have to justify it. I did that with one of them. Just show that you know second derivative is positive, so the graph is concave up, so it's an underpart. All right, so that's one kind. This one, I tell you the function, and you figured out where to. I don't remember if I told you where to draw the tangent line or not. Yeah. Am I? I did need to read for it. I think I am. No, I am. I'm recording. I don't know what. I know. And then the kids in the other class say, you go off on so many tangents when you record. I know, right? So now the other type is where I'm a little bit more vague. I don't even tell you the function. I don't tell you where to draw the linearization, write the linearization. You just got to know it. So that was like, yeah, the square root of 15. Well, let's do a different one. Give me one that we could approximate, something you don't know. The square root of 27? Cube root of 27. Like it. So let's say we have we're asked to approximate the cube. Wait, the cube root of 27, we know that. Okay, 24. All right, fine. No, we're going 24. Okay, we're going to approximate the cube root of 24 with a linearization. Now, first of all, identify the function. What is this? What would the function be? Cube root of x. You just replace the number there that was plugged in. Now, so if you have the cube root of x, f of the cube root of 24 is just f of 24. It's the y coordinate on the graph when the x coordinate is 24. That's the actual cube root of 24. We don't know it. But is there a number near 24 that we do know the cube root of? Because that's where we're going to write the tangent. 27. So we're going to write the equation of the tangent line at 27 and then pop the 24 in. Right? So you write the equation of the tangent line at a value that you could plug in and know the answer. It has to be nearby. So that's where we're going to write the equation of the tangent line. So when I write the equation of the tangent line at 27, how am I going to get the slope? What is the slope going to be? Like, you don't have to say what number it is, but it's going to be, is it f or f prime? F prime of 27. You're only going to use 27. You're going to only use that number, the nearby number you know. What goes in the parentheses? Okay, and then what do we have at the end? Plus f of 27. Good. So we have to figure out, to write the equation of tangent line, we have to know the slope and the y one. So what's f of 27? That's the easier one. 3. Root 27 is 3. So now we just got to get the derivative so we can get the slope. F prime of x. That's x to the third. So the derivative is 1/3 x to the negative 2/3. So I like what you're saying, though. You're saying 1/3 cube root of x squared. Nice. Now we'll plug 27 into that. One over 3 times the cube root of 27 squared. Cube root of 27 squared. Well, what's the cube root of 27? 3. You square that. 9 times 3. So we get a slope 1/27. Okay, we're almost there. So that's the equation on the tangent line. We're trying to approximate the cube root of 24. What do we plug in for x? 24. I always get the kids who are trying to plug in the cube root of 24. No, the function does the cube root part, all right? You're just plugging in the x value into the equation of the tangent line. So you're not going to be plugging in any weird things. You're just going to be plugging in some integer, whatever it is. So f of 24, which is equal to the cube root of 24, is approximately equal to 127 times 24 minus 27 plus 3. Oh, that's kind of nice the way it worked out. Let's do what's in the parentheses first. 24 minus 27, negative 3. So we have negative 3 27ths, or negative 1/9 plus 3. Now, if we want to get a common denominator and combine them, yeah, well, I don't need to say that. How many ninths are there in 3? So negative 1/9 plus 27 ninths, 26 ninths. It's tough, right? All you're doing is writing the equation of a tangent line and plugging a number in. And in this case, do you think that that's less than the actual or greater than the actual? Greater, because this one's going to be concave down. We know what the cube root of x looks like. The function's concave down for values of x between 24 and 27. So is that part okay? Linearization, tangent line. This sounds so complicated. That's no, not even near. No, well, it's not going to get more difficult for those. Those are not. Yeah, that type. Optimization. What kind you want to see? All of them. Yeah. Well, you weren't here for any of this, so what am I going to do? I'm keeping to the ones that we focused on in class. So people that were here in class are good. Tell me one that we did in class. Tell me when we spent some time in class, and I'll. Okay, we could do one of those. Do one of those cut ones. Yeah, I don't know how to do optimization. If you cut like the squares, the box, that was the basic one. Can, good. You guys are picking good ones. Okay, guys, with optimization problems, when you're asked to find the greatest or the least value of some function, you got to get an equation for that function, right? And it's got to be in how many variables? 1, right? That one has to be in one variable, optimization. Now, at that point, you could technically, although you won't get credit on the test, pop it into your calculator. And whether you're asked for a max or a min, you're just going to find out where the derivative equals 0. So you got to just write an equation for whatever you're trying to optimize. You might need a second equation to substitute to get it in one variable. But after that, you just set the derivative equal to 0 and solve. Okay, so you guys were mentioning there was poster, box, can. I don't know. The pool one, the poster one, it's the same thing. Okay, so the pool one, what number is that? pool and the post are exact same problem. I don't know, they want to do this one. All right, so you have a pool. You want to put your like cheese lounge chairs out like at the end. So you want to have like 8 feet deck over here on the side. You just need 4 feet of decking. And the pool, what was the area of the swimming pool? So this had to cover 800 square feet. So we know the area of the actual pool water, okay? But what we're trying to minimize is the amount of land used, the overall, not just, we already know the area of the actual water part of the pool, right? That's 800 square feet. We're trying to minimize the area of this big rectangle here, the area of the rectangle, including the pool and the decking. So I have to I already know the decking, those dimensions, but I have to put on, I don't know what the width of the actual pool is here. So what do you want to call it? Love it. And what about the length of the actual pool? Okay. All right. Now, what's important, though, is you first write the equation of what you're trying to optimize. We say we're trying to minimize the amount of land use, which is the area of the big rectangle. So it's got to be, it's length times width. Okay, I'll write length times width. We can't keep that. Let's say we call this the length. This whole thing. This 8, this y, this 8. Let's call all this the length. Yeah, that's y plus 16. And let's say the width is this dimension. So what is it? X plus 8, because you got 4 plus x plus 4, x plus 8. That's what we call your primary equation. That's the equation that we got to eventually get in one variable, take the derivative and set it equal to 0, because we're trying to optimize the area. But the only problem is, what do you see when you have this before? 2 variables. That's why they have to give you some other information to write a second equation so you can substitute in there and get it in terms of one variable. So what's the extra info they gave us? X what? Times y equals 800, right? Because they gave us the area of the pool, that we know that x times y equals 800. That's that secondary equation we can write so we can solve for one of those variables. And now, do you want to solve for x or for y? Oh, you guys, that's nice. So x is equal to 800 over y. Okay, so we're going to go put that in for the x over here. Then it'll only be in terms of one variable. Oops, don't. Okay. So we have it in one variable. What's that? Yeah, you got to clean it out before you, and then we'll take the derivative. You could technically take the derivative now. It just, you have to use product rule. All right, so we haven't taken the derivative yet. What's first times first? 800. Outside times outside. Y inside times inside. Whoa. 16 times 800 over y. 1, 2, 8. Is it? All right, and then last 12,800 over y. And then 16 times 8. And I'm not even going to combine those constants. Call me crazy. Because we're going to be taking the derivative anyway, right? We need to combine those. So please don't set the function equal to 0. 7 kids will do that tomorrow. Experience. You got to get the derivative. You don't want to know where the area is 0. That's crazy. You want to know the slope. If you're looking for minimum area, you want to know where the slope. So take that derivative first. Okay, so we're not going to write the zeros. How about for the 8y? 8. What about the derivative of that? Nice. All right. And we set this equal to, we want to get a min or a max, we set the derivative equal to 0. And it's so nice when we do these because we often wind up with a positive term and a negative term. So what do we love to do? We're not rejecting anything. We bring the negative stuff. We add whatever. We have a negative term, we add its opposite to both sides. Yeah. So we set A equal to 12800 over y squared. We just added 12,800 over y squared to both sides. And then what? Cross multiply. Right, that's over 1. So you have 8y squared equals 12,800. Divide by 8. I don't know what to do. Oh, okay. Sorry. I didn't remember that. All right. Now, so y squared, I'm sorry. What was that? Y squared equals 1,600. Now, normally, we take plus or minus the square root. We're not crazy. But what we didn't say here, the restrictions, what does y have to be? Positive, right? So we're only going to take the positive square root, which is 40. Now, because we did the same thing to find a max or a min, we got to make sure we have a min, not a max. So we just, where's my A prime? Right here. So we know, I'm going to make a little sign chart for A prime, right next to A prime. We know it's greater than 0, but we got 40. Give me a number between 0 and 40. 1 is the answer. And when you plug 1 in for y, is the first derivative positive or negative? Give me a number greater than 40. 1 million. If y is 1 million, so we did A prime of 1. Here we'll do A prime of, I'm just going to write mil because I can't fit. Okay. If you plug in 1 million into your first derivative, is it positive or negative? Positive, right? So do we have a minimum area? It goes from negative to positive. Okay, so we know that to get a minimum area, we want y to equal 40. And if we're asked for the dimensions, how are we going to get x? Yeah, 800 over 40 would be 20. But x and y are not the overall dimensions. They're the dimensions of the pool. Remember the overall dimensions we started way back when? Yeah. So the length we said was y plus 16. So 56. Would be 56 feet. That would be length by 28 feet. Yes. Sure. Exactly. These are still the overall dimensions. Nice. Never get that. All right. What do you want to do now? Volume, can, any of those? All right. 8 from the review sheet. I'm going to look and see if I like it. Skip it. Related rate problem. What did you want to do? Yeah, I would know that one. All right, six will only take a minute, but I do think it's probably smart you do. The can problem. Remember we did the soda can problem? You have a right circular cylinder. It's a can. It happens to be holding 10 cubic inches of sea monkeys. They don't advertise sea monkeys anymore in magazines. This is a can of sea monkeys. It's holding 10 cubic inches. And you have to minimize the surface area. So, what is my primary equation? Surface area, which is given to you, right? It's 2 pi r squared plus 2 pi r h. That's the one you have to get in one variable and set the derivative equal to 0. All right? But it's in 2 variables. So you say to yourself, they must have given me some other information so I can get that one in one variable. What's the other information they gave you? What is this? 10 cubic inches. Volume. So they didn't say the volume is, they just said it contains 10 cubic inches of sea monkeys, but you have to know cubic inches is always volume. So the volume has to equal 10, and the volume of one of these cans is, it's given to you, pi r squared h. That's your secondary equation. You're going to use that guy to substitute into your primary equation. No? Wait, am I losing here? You see that this is the volume? This is the one we want to get in one variable. Ah. All right, I was a little worried. So, what do we want to substitute in for? What do we want to solve for in this one? Solve for h. We'll solve for h here. We'll plug it in there. We'll take the derivative and set it equal to 0. Right? So if we solve for h here, we get h equals 10 over pi r squared. So put that in over there. So the surface area is equal to 2 pi r squared plus 2 pi r 10 over pi r squared. Always clean it up before you differentiate. What can we get rid of or cancel? Pi, and one more thing, one of the r's. We still have an r down there. So our surface area is equal to 2 pi r squared. What's the next term? 20 over r. Now we just got to get the derivative and set it equal to 0. Easy breezy. All right, what's the derivative of the first term? 4 pi r. And the second term? I like how you guys are getting good at that. Minus 20 over r squared. And what do we do with this derivative? Yeah, we thought of this as 20r to the negative 1, if you're wondering how we got this. So it's negative 20r to the negative 2. That's where this derivative comes from. All right, I'm just crossing out some part. Okay, so yeah, well, now we want to set the derivative equal to 0, right? We're going to set 4 pi r minus, we're interested in knowing where the slope equals 0. It doesn't matter whether we're looking for a max or a min. We do the same thing. Oh, look, we got a positive term and a negative term. Move the negative one over there, so we have 4 pi r equals 20 over r squared. Why? Oh, I disappeared. Okay, cross multiply. Go ahead and do that while I'm figuring out where I am. Found it. All right. All right, so we have 4 pi r cubed equals 20. Divide by 4 pi. So r cubed, we could reduce this to 5 over pi. Is that okay? If r cubed equals 5 over pi, what does r equal? The cube root. That's a nice looking radius. Uh-oh, what if this gave us a maximum surface area? We better check. 5 over pi, let's say it's like 5/3. The cube root is going to be between what two numbers? Cube root of like 5/3, greater than 1, less than the cube root of 8, right? Some number between 1 and 2. Cube root, where is my 8 prime? We'll go right here. So we knew the radius had to be greater than 0. And we had the cube root of 5 over pi, which is a number between 1 and 2. So when you're taking your test values, over here, I could take like 1. If the radius is 1, is 8 prime positive or negative? Negative. If the radius is greater than that, like 50, positive, right? So do we have a max or a min surface area when r is the cube root of 5 over 5? Min. So we have a minimum area when r equals the cube root of 5 over pi. And if they want the height is just 10 over pi times that squared. The cube root of 5 over, you don't even have to simplify it. If you put things into your calculator, and I'll write this on the test, just round to 3 places after the decimal. Yes? I would go back and check your work because it'll never happen. Yeah, but if you got like 2 critical values, you'd have to see which one was the min and which was the max, but I don't have anything like that. Nope. Yes, you want to show that, because only because you're doing the same thing to find our max or min, so you really want to see that you're getting the one you were looking for, but it always turns out to be that way. Not to ruin the story, I want you to be excited when, oh yay, it worked out. Tell me the related rates problems that you think we've stressed most in class. You guys are excellent. You're good thinkers. The cone I had to put on that. I'm trying to think if there are any others. Yeah, I know. I just was afraid of the time because these word problems take, yeah, because you need to do the substitution with the similar triangles. Yeah. Yeah, and I would think of the related rates homework problems that we went over yesterday. But one of the questions that somebody asked in here, think about the ones we went over. Should be. I'm glad. And I have extra help after school if you need more. Let's see, where are we going here?